MAP4C 5.0 graphical models. What we're going to do in this chapter is investigate linear, quadratic, and exponential relations as equations, as a table of values, see some of their applications, as well as develop regression models that fit this type of data. So, to start off with linear relations, the graph of a linear relation is a straight line. And the equation of the line is y is equal to mx plus b, where m is the slope, which is described as its rise over run. So the rise is the vertical change between 2 points, and the run is the horizontal change between 2 points. We can refer to the point on the left as x1, y1. Notice that subscripts are names in mathematics. And then the second point is x2, y2, as given as an ordered pair. So in this equation, that describes the slope, and that slope would be the same between any 2 points that belong on this line. B is the y-intercept, which is where it crosses the y-axis. So on that vertical y-axis, where does that line cross? In this case, it would be 40. A quadratic relation. The graph of a quadratic relation is a parabola. So a parabola has this U shape. This one right here is a maximum because at the top, that's the highest point for our vertex. The opposite is a minimum. But what we're going to do is look at the different forms of a quadratic equation and see what it reveals about this parabola. Starting off with standard form. The only feature that is revealed from standard form is C, the y-intercept. Because when we let x equal 0, notice it's positive here for x, negative over here, but when x is equal to 0, that's going to be the value that's on the y-axis. So we can think of C, just by inspection in standard form, as the y-intercept. So notice it's 3 terms, and we have a descending power. We have degree 2, degree 1, and then there's no x, so we call that degree 0. This is a degree 2 polynomial, meaning that the highest degree of any term is x squared. Vertex form, remember that the vertex is this point, in this case it's a maximum, is a critical point. Usually something interesting happens. In this case here, we have number of sweatshirts produced versus profit. This is telling us that the maximum profit occurs when there's a certain number of shirts produced, approximately in this case 750. So this form reveals that component of our parabola, which is usually important. So h and k is the coordinate, or are the coordinates of the vertex. Next, factored form. In some cases, we are interested in the x-intercepts. Now think about it this way. When y is positive, we go up. When y is negative, we go down. But when we're on the x-axis, the value of y would be equal to 0. So how can we solve this complex equation for when y is equal to 0? Well, we're going to take advantage of the zero product property. That means that if one of the factors, numbers used to multiply, is equal to 0, then the product is equal to 0. For example, 5 times 0 is 0. 1,000,000 times 0 is 0. So what we need to look at is what values will make each of these brackets equal to 0. And those will be the instances in this equation when the parabola crosses the x-axis. So R and S are x-intercepts. Now quadratics are interesting in the sense that they show up in some seemingly unrelated topics we've already investigated with optimization of areas. Here we can see as part of a profit function, as well as projectiles, so objects that are thrown into the air. Lastly, exponential relations. The graph of an exponential relation is an exponential curve. So to see that visually, it looks like this right here. It's increasing gradually at first and then more rapidly, or it can rapidly decrease and then gradually decrease. Notice in both of these cases it's approaching the x-axis but not crossing. We call that a horizontal asymptote. The equation of an exponential equation looks like the following. Y is equal to ab to the power x. So a is the coefficient, where a is the initial value. So where does it start? That's also the y-axis, y-intercept on the y-axis. B is the growth factor. So the growth factor refers to what is the pattern that describes the growth? What percentage change is it? And it's helpful to think of this as percentage change for many financial applications. So, exponential growth. We have it in the form y is equal to ab to the power x, but this is determined by the value of b. And if b is greater than 1, then we have exponential growth. So if we were to think of, for example, 10% growth, we could multiply a value by 1.10, because 1 is the initial value, and that 0.10 is an additional 10%. So if we use that factor to talk about percentage growth or percentage decrease, we can think about this right here, b to the power x. We use an exponent to discuss repeated multiplication. And if we have repeated growth by a percent, then we can use that factor, b, to replicate that multiplication, x times. So whenever we multiply by a value greater than 1, we'll get a larger number. And therefore, that's why we would expect to see exponential growth. Whenever we multiply by a value that's between 0 and 1, so think about, for example, 0.5. When you multiply by 0.5 repeatedly, we could start off with 1, and then we would get half, and then a quarter, and then an eighth, and so on. And that value would decrease over time and would approach 0, but never actually reaching 0, because by definition you always have half of the original amount. So there's still something there, therefore a horizontal asymptote on the x-axis. And this is referred to as exponential decay. So exponential growth can model a lot of natural processes when it comes to populations, for example, and whether that's people or bacteria. Exponential growth is a very common way of describing growth as a percentage. In exponential decay, we can use this for applications like half-life of a substance to describe changes over time. For example, this exponential graph shows the mass of pain medication left in a person's bloodstream after a tablet is swallowed. So investigating the graph, we see exponential decay. We see an initial value of 500. Pain medication in the body. How much medication was initially taken? So when time is 0 on the x-axis, so that's the beginning. The initial value is 500. Determine the ratio of the mass of medication after 1 hour to the mass of medication after 0 hours. What does this value represent? So at 0 hours we're at 500, and after 1 hour we're at 400. And what this represents is the decay factor. So we can find the growth or decay factor by calculating the ratio of any two successive y values. So divide points that are next to one another to find out their growth factor. In this graph, the masses after 0 hours and 1 hour are easiest to read. The vertical intercept represents the mass of medication initially taken, and we said that that was 500 milligrams. And the decay factor is the mass of medication after 1 hour divided by the mass of medication after 0 hours. So we said that that was 400 and 500, which is equal to 0.8 when we divide this rate. So each hour, the mass of medication remaining in the body decreases by a factor of 0.8. And you can see that that is consistent in this graph.